Recording, so it is underway, and I'm gonna share my screen again. Give me a second. Okay. All right, so Ee407. Today is the 30th, I guess. November 30th, Monday. All right, so we started looking at PID controllers, right? And we started with the proportional only controller, okay? PID controllers. Oops. Sorry about that. It's kind of an overshooted writing. So we said case one, P controller. And remember that we were looking at, let me resketch our configuration. We are considering that our controller is just in front of the plant, which is often the case, okay? Because the controller is actually acting on the error signal E, okay? We have a reference signal, we measure the system output and compare it with the reference to generate the error signal. And we had also G of S given by a particular example where we had two stable poles, right? S plus 1, S plus 2. Okay, and what we have seen for the P controller is that the root locus, right? Here are the two stable poles of our system, our open loop system, right? At -1 and -2. So what we have shown is that the root locus actually is, this region over here. So it starts with the open loop poles meet at the breakaway point, and then was actually coinciding with the asymptotes. Okay, branches in this case coincide with asymptotes at plus 90 and minus 90 degrees. Okay, so this is our S plane, this is the real part, and this is J omega axis, okay, imaginary part. So what was happening is that with P controller, right, this is our, remember that GC of S was equal to KC for the proportional controller, and at KC equals 0, this root locus starts here and moves on as KC is increased. It was moving towards infinity on top of the asymptotes. Okay, and obviously we, although we are not we do not too much focus on negative gains, but you can also know that for negative KC, okay, the root locus will have a different shape, but it's going to eventually cross to the unstable side. Okay, so for example, what's happening with KC negative, we have seen we can work on the Raut-Horwitz criterion, which will also tell us, for example, when KC, what value of KC actually makes this system unstable. It's going to be a negative gain. Okay. Anyway, that's not our focus, but positive gain in this case is our focus, and we basically have said that the system is always stable. Okay, and then the system was actually having a settling time which was equal to approximately 3 over psi omega n, and for any pair of complex conjugate poles over here, okay, at a particular kc value, right, this point over here, the projection to the j omega axis, the projection to the real axis was psi omega n with a minus sign, okay, and therefore the settling time actually is starts with a larger value, right? Starts with Ts equals 3 over minus 1, 1 basically 3 seconds, and improves until Ts is equal to 3 over this point over here, the breakaway point, where we have this is minus 1.5, so 3 over 1.5 is equal to 2 seconds, and stays constant for larger Kc. Okay. Any questions so far? So in terms of the settling time, the PD controller, the P controller here, the proportional controller, actually gives us an always stable system with a settling time that starts at 3 seconds. If we increase the gain, the settling time improves until it is 2 seconds, which happens at the breakaway point. And then afterwards, because the projection to the real axis stays the same, the settling time does not improve anymore. So this is the best settling time that can be achieved with this system. Okay. So settling time cannot be improved below Ts equals 2 seconds. Okay, so that basically is one of our limitations with this system. Remember, the question was that we want to find a controller that will achieve a settling time which is as small as possible and a steady state error as small as possible. So I want to take a look at the steady state error as well at this point. Okay, any questions so far? So you see that with a proportional controller, if I have two stable poles, I remain in the stable region always. So the system is always stable with an open loop stable poles. While if I was starting with a system with unstable open loop poles, that means two poles on the right hand side for G of S, the proportional controller actually would not be able to stabilize this system, right? Because if the two open loop poles were already unstable and the asymptotes plus 90 degrees, minus 90 degrees asymptote would be just in between the two poles again. So the system would always be unstable. So I would have been unable to stabilize this system with the proportional only controller. So in this case, because the system is already stable, I can remain in the stable region and I can play around with the behavior of the system. But we see that settling time can be only improved until 2 seconds and no better. And we don't yet know what's happening with the steady state error. Okay, so what about steady state error? First, you guys tell me what is the type of this system with the controller? So remember, GC of S G of S is actually equal to KC times 1 over S plus 1, S plus 2. So what is the type of this system?
No, type 2.
Really? Don't confuse type with the order of the system.
Type 0. Çarpanıyor.
It's a type 0 system, right? This is a second order type 0 system. It's second order. Don't confuse the order with the type. Type 0 because no standalone integrator in the denominator, right? So that's correct. It's a type 0 system, so we will have a steady state error. What is the steady state error for a type 0 system? In this case, it will be 1 over 1 plus Kc over 2. Okay? And you can derive this from either limit of the error, or you can just find out the limit of the output and you can compare it with your reference signal. Okay? And remember that if we want to take the time limit of a time domain signal, we can also find that if the signal converges by taking the limit in the Laplace domain, a different limit in the Laplace domain. Okay? All right, so what does that error means? That means ESS will actually be decreased with Kc increasing. So so that tells me increase Kc to improve ESS. Okay? But is that the only effect we have? Okay, let us see what's happening. Now, what's happening if I increase Kc? Remember the root locus. So if I increase Kc beyond the breakaway point, so Kc will increase and steady state error will decrease. But see what's happening.
Overshoot increase.
Very good, right? So what's happening is that both, remember, this is omega n, this length, and also this is j omega d. Okay? What was omega d? Omega d is damped natural frequency. Otherwise, it is the frequency of damped oscillations, the frequency of oscillations within the exponential envelope. Okay, so what we have here is that if I increase Kc, omega n will increase, omega d will increase with constant exponential envelope. Now, what does that mean? Let me show you why, but as your friend have suggested, oscillations, and as a consequence, and I'm going to show you in a figure in a minute, overshoot will get worse, will increase, okay? Increase. Why is that the case? Well, because you have a constant envelope, exponential envelope. Remember, this is your reference signal, let's say. Okay? And obviously there will be a steady state error, so the system will not converge to the reference, but to a different value. But here's what's going to happen. There is an exponential envelope around this steady state value. And let's say that this is your settling time. Settling time is constant. Okay, you increase Kc, settling time doesn't change because the exponential envelope is constant. Exponential envelope. But if this is your, let's say, if this is your response, as you increase Kc, these will be squeezed, increasing Kc. What's going to happen is that the frequency of oscillations will increase. Therefore, the response will be squeezed within this envelope. Let me sketch one more. Okay, so as the frequency increases, you see that overshoot over here. Okay, larger overshoot. Okay, so yes, the system is always stable, but in the sense of not becoming unstable. Okay, but if you think about how the system behaves, if you increase the gain, there will be faster and faster oscillations, and there will be larger and larger overshoot. Okay, so in a sense, this system is not very desirable. Would you agree? So large overshoot.
Hocam şeyi ne belirliyordu o envelopu?
Now the envelope is determined by, remember, the exponential component of the response, and the exponential component is determined by the real part of the poles. Okay, so because after the breakaway point, the real part psi omega n is constant, therefore the value at the exponent of you have, remember, you have e to the power minus psi omega n t. So psi omega n is what determines the exponential envelope, and it's going to become, it's going to start as a slow exponential. It's going to become a faster exponential, but at 2 seconds settling time. After that point, if you increase Kc, exponential envelope will be constant. All right? So large overshoots and fast oscillations are quite undesirable in most applications and limit us from increasing Kc further. I mean, you know, it really depends on the application. In some applications, making the system faster at the expense of larger oscillations might be acceptable, but there are many other applications where this is clearly undesirable. Let me give you some examples. In fact, examples that we have discussed before. For example, an elevator position control problem. I mean, think about tuning your controller for an elevator, right? You want to arrive at the desired floor relatively fast, but think about this behavior over here. You cannot make it too fast. And what is the steady state error? Steady state error is that small kind of discrepancy between the floor and the elevator floor, right? Often that's an annoying thing to have. But if you have this kind of behavior with very large gain, what you will have is that when you arrive at the floor, you will have this oscillation, and you will not stop at the floor, but have this very annoying oscillation with a large magnitude. Okay, so often in an elevator position control problem, you select a steady state error that you would accept, and you will live with that instead of having or introducing very large oscillations. Okay, In another process, which is, for example, controlling the thickness of metal sheet production. Okay, so you are generating a metal sheet at a constant thickness. So a steady state error would have you have the thickness in the vicinity of the desired value, but with a small error. But overshoot and oscillations would mean that the thickness is not consistent. It's going to have bumps and valleys in the production. So that is much more undesirable as compared to a small error in the thickness. Okay? So, that the message is that it's not always desirable to make ESS very small. You just want to make it as small as required by the application while maintaining a reasonable or sometimes non-existent overshoot. Okay?
Hocam,
Yes.
Biz grafikte özel olarak belirtmedik ama sarı grafiğin ISS'i daha düşük olacak değil mi? Yani steple ilk ISS arasında bir yerde olacak.
Hayır, öyle olmayacak. Çünkü sonuçta şeyi varsayıyoruz. Ne zaman osilasyonlar başlıyor? Ben artık complex plane'e geçtikten sonra, yani şurada. Değil mi?
Evet.
Bu noktadan sonra artık ISS'de özür dilerim. TS gibi algılıyorum. ISS küçülmeye devam edecek. Evet. Ben KC'yi arttırdıkça ISS şu formülle küçülmeye devam edecek. Ama artık kabul edilemez derecede osilasyon ve overshoot almaya başlamış oluyor.
Anladım.
Is there any other questions?
Exponential envelope değişmiyor dedik yani o polünün.
Belli bir noktadan sonra evet. Yani osilasyon başladıktan sonra exponential envelope değişmiyor artık.
Peki ISS o zaman nasıl değişiyor? Yani ISS'in
ISS ile TS'i ben biraz önce karıştırdım. Settling time ile steady state error farklı şeyler. Settling time real part'a bağlı. Yani exponential envelope'a TS bağlı. Dikkat edin. Envelope sabit kaldıkça settling time değişmiyor. Sabit. 2 saniyeden sonra iyileşmiyor. Ama öte yandan steady state error formülü KC ile ters orantılı. Cevap oldu mu?
Evet oldu.
Başka soru var mı arkadaşlar?
Hocam bir de DC gain de değişiyor değil mi? İkisini aynı yere çizdik.
DC gain nedir? DC gain aslında steady state error ile ilişkili. DC gain şu demek. Siz referans input'ta bir değer veriyorsunuz ama output başka bir yere converge ediyor. Aradaki fark DC gain olmuş oluyor. Ama aynı zamanda da steady state error olmuş oluyor. Doğru mu? Yani ben 1 veriyorum referans olarak. Output 2'ye converge ediyor. O zaman DC gain 2 olmuş oluyor. Değil mi? Steady state error de şey olmuş oluyor işte. Output'un steady state değeri eksi referansın steady state değeri de steady state error'um olmuş oluyor.
Hocam bu exponential envelope şifretmeyecek biraz KC arttıkça.
Sizi duymakta zorlanıyorum.
Exponential envelope şifretmeyecek mi 1'e doğru KC arttıkça?
Exponential envelope şu noktadan sonra artık değişmiyor. Şu breakaway noktasından sonra şurada, şu breakaway noktasından sonra real part sabit olduğu için exponential envelope da artık sabitlenmiş oluyor.
Ama exponential envelope'un converge ettiği değer steady state değer oluyor ve steady state'de KC'li değiştiğine göre exponential envelope'un değişmesi gerekiyor.
Envelope kayıyor diyebilirsiniz, doğru. Yukarı aşağı kayıyor ama şekli hiç değişmiyor. Doğru mu? Ama haklısınız. tıpatıp aynı yerde durmuyor. Steady state error ile birlikte, yani output'un steady state değeri etrafında tanımlı olduğu için şekli değişmemekle birlikte yukarı aşağı oynuyor. Unutmayın, TS neyle tanımlıydı? Percent değerle tanımlıydı. Yani şuradaki band tanımladığımız şu band var ya, buraya mesela şöyle diyoruz, 5% band. Dolayısıyla ben yukarı gittikçe o band genişliyor ama percentage olarak sabit kalıyor. Doğru mu?
Doğru.
Ama haklısınız yani söylediğinizde, çünkü burada sanki steady state değeri de sabitmiş gibi gösterdik üst üste çizebilmek için. Note: as Kc increases, the exponential decay rate is constant, but this shifts up down with y steady state. Bilmiyorum anlaşılır oldu mu? Biraz eksik oldu ama aynı zamanda expand de ediyor orantısal olarak. Soru var mı? Okay.
Hocam ben şey soracaktım da, bu ikisi de zaten 5'te ya. Hani yani 5 aynı yükseklik oluyor. İkisi de o yüksekliğe aynı anda girmedikleri için, ya o yüksekliğin limitine girdikleri an mı biz TS kabul ediyoruz? O pikleri mesela o 5 bandına girdi, yüksekliğe değdi. Tamam, bu settle oldu.
Gerçek güzel bir soru. 302'de biraz tartışılmıştı. Gerçek tam exact settling time aslında oscille eden o sinyalin bandın içine girdiği an. Ama biz onu approximate ediyoruz. Nasıl approximate ediyoruz? Exponential function'ın bandın içine girdiği an olarak approximate ediyoruz. Yani şeyi umursamıyoruz. Osilasyon tam olarak ne zaman girdi? Osilasyonun magnitude'unun onun içine girdiği anı kabul ediyoruz.
Bu ikisi de aynı gelmez mi? Envelope aynı oldu.
Bu envelope aynı ama şey olabilir, yani özellikle daha erken girdiği veya daha geç daha geç giremez ama daha erken girebilir.
Ama işte o zaman da osilasyonun peak'ine bakmamız gerekmiyor. Sadece envelope
Bakmıyoruz işte, basitleştiriyoruz. Bakamıyoruz çünkü o anı bulmak çok daha karmaşık bir hesap gerektiriyor.
Ama burada işte envelope'u bulunca ikisinde de aynı gelmezdi. Çünkü envelope aynı anda girmiyor. Aynı şey oluyor.
Ama şöyle girebilir mesela. Yani bir örnek verelim mesela. Diyelim ki envelope şöyle. Envelope şurada giriyor bandın içine. Değil mi? Bir şey çizmeye çalışalım mesela. Mesela ben şimdi daha erken sokacağım içine. Daha erken sokabiliyor muyum? Sokabilirim. Şöyle olması lazım. Bir saniye. Nasıl yapacağız? Daha doğrusu şöyle yapayım. Öyle bir bant çizeyim ki, şimdi şöyle osilasyonu çizelim. Öyle bir bant çizeceğim ki şey olacak. O bandın içine şey daha erken girecek. Şöyle diyelim mesela. Şöyle çizsek. Şimdi ben exponential function bandın içine şu noktada giriyor ama fonksiyon bandın içine şurada giriyor. Çok güzel bir örnek olmadı ama ne demek istediğimi anlatabiliyorum diye düşünüyorum. Yani sinüsün kendisi bandın içine daha erken girebilir. Peak noktasında değil, arada bir yerde girebilir. Anlatabiliyor muyum?
zaman hani o farkı, ikisi arasındaki farkı grafik olarak tam gösteremiyoruz.
Hayır, şöyle, yani sonuçta bir simülasyon yaparak MATLAB'de çizdirdiğinizde bandın içine girip de bir daha çıkmadığı ilk an gerçek settling time oluyor. Simülasyonda bunu görebilirsiniz. Üzerine exponential function'ı çizdirdiğinizde exponential function bandın içine biraz daha geç girebilir. Ama biz elle hesaplarken, çünkü exponential function'ı kullanarak TS için yaklaşık bir değeri rahatlıkla bulabildiğimiz için o şekilde bir derivation yapıldı. Ama simülasyonda hani ilk defa bandın içine girip de bir daha çıkmadığı anı gerçek settling time olarak alabilirsiniz. Tamam? Okay. Let's continue. So now let's take a look at what we can achieve with actually adding new controller actions. Okay, so let's discuss proportional derivative or PD control. A very popular controller combination, actually. Okay, very popular. In fact, all of these combinations are very popular, but in this case, GC of S, the controller transfer function, is a proportional constant plus Kc tau d times S. Okay, so this is our proportional gain. And this whole thing is the derivative gain. Okay, but tau d is known as derivative time constant. Okay, so the combination of the derivative time constant with the proportional gain becomes the derivative gain. Okay, remember we had given this type of controller parameterization a name that was dependent ideal PID form, right? So this is an example of, again, dependent ideal PID form. Okay. Now, what does that mean? This means that I have GC of S given by, if I take it into Kc tau d parentheses, I will have S plus 1 over tau d. This is why actually this is known as the derivative time constant, because you see that it directly becomes a new zero in the system. Let's call this combination Kd, the derivative gain. So I have S plus alpha. Okay, remember that this is a constant in this case. So it's a selection, actually, a selection. And this is usually how we design a PD controller. We make a choice for alpha, and we still deal with the root locus for KD. Remember, root locus is a method where we can only vary one parameter and see what's happening with the closed loop poles. In this case, by fixing alpha, I have KD to play with. Okay? So, notes. PD controller introduces a new zero to the open loop transfer function. Okay, so now I have a new zero. Okay, what is my open loop transfer function? GC of S, G of S becomes now KD S plus alpha, S plus 1, S plus 2, and alpha is defined as 1 over tau d. It's a choice because it's the parameter of the derivative controller. Okay, we can choose what tau d should be, and henceforth we can choose what alpha would be. Okay. Now let's continue with our root locus method, because that shows us now sketch what happens with chosen alpha in the root locus with respect to KD. Okay. Now let's take a look at number of asymptotes. Our usual procedure, right? We have n minus m absolute value. Here I have two poles and 1 0. Therefore, I have one asymptote. So you see, the number of asymptotes was reduced by 1 by the introduction of a 0, because I had two poles and two asymptotes. Now I have one more 0, so that takes away from one of the asymptotes. Okay, and therefore I have one asymptote. What is the angle of the asymptotes? Because I have now one asymptote, okay, remember the formula, plus minus 180 degrees over n minus m, 2l plus 1, odd number of angles. In this case, n minus m absolute value is 1, therefore I have plus minus 180 degrees. Okay, which corresponds to the single asymptote. It's the negative real axis. Okay, so let us sketch. Obviously, it really depends on where the 0 is. Okay, but let's assume that minus alpha is over here. Okay, so alpha is a positive number and minus alpha is smaller than the two poles at minus 1 and minus 2. So what is the part of the real axis that is part of the root locus? This region, because I have odd number of poles and zeros at the right of the chosen point, and also over here. Okay, remember that root locus starts at open loop poles and have to end up at the open loop zeros. Okay, and the only asymptote is on the real negative real axis. This is the only asymptote. What I need to have is that I will need to have a breakaway point here, and I will have to have a break-in point here, because I still have two branches. Remember, number of branches equals max mn equals to 2. So I still have two branches, but I have one asymptote. So one of the branches necessarily need to go to the 0. The other branch will go to the asymptote. Okay, so after this break-in point over here, one branch will be going to the 0, the other branch will be going towards the asymptote. Okay, again, what was my parameter was KD 0 here, KD 0, and here KD goes to infinity, and over here KD goes to infinity. Okay, so the branches will approach the asymptote and the 0. Any questions with the root locus? Obviously, you need to be able to sketch the root locus in order to make such an analysis. Okay, but let's take a look at first the root locus. Okay, now is it better or worse than the previous case? And in what respect, you think? So let's take a look at the settling time first. Okay. Now let's see what's happening. So the poles start at here, right? So over here, the dominant pole is the one nearest the j omega axis. Okay. So settling time starts to become smaller as I move towards the right, towards the left. Okay. Then I branch away to the two sides, but the real part, the one determining the exponential decay, keeps decreasing, correct? Let me choose a different color. Is my pointer visible? Okay. So I move towards the left, okay? And therefore the settling time is reduced as I move the real part towards the negative with larger magnitudes, okay? So as I move this way, okay, poles moving left means better settling time. Why? Because psi omega n becomes larger. Okay, so psi omega n increases, Ts equals 3 over psi omega n becomes smaller. Better settling time. Okay, what happens after this point over here? Okay, so maybe this part might not be correct, as I'm gonna explain in a minute. So the poles are meeting at the break-in point. What's happening afterwards?
Settling time becomes worse because psi omega decreases.
Okay, very good, right? Let's call this a minus beta point. After this point, right, one of the poles start actually moving in the opposite direction, increasing the dominant behavior of the poles, right? In the sense that psi omega n actually starts decreasing again for the dominant pole, okay? So Ts improves until break-in point at minus beta, after which one of the poles, dominant one starts moving towards j omega axis, reducing again dominant psi omega n value. Okay, let's say increasing Ts. So S12 at minus beta is the best, or gives us the best, right? Gives us the best settling time. Any questions so far? So furthermore, the system is becoming more and more stable, right? Because our poles are moving away from the j omega axis. What about oscillations? What about oscillations in the system? Is the overshoot? What about the overshoot and the oscillation frequencies?
Real şeyde olduğu zaman pole oscillation'da sanki sıfırlanıyor.
When we are on the real axis, no oscillations. It's an overdamped system. When we are in the S-plane as a complex conjugate pair, right? we have some oscillations. What's happening here, for example, as I move on that circle over here? What's happening with the oscillations?
First increase, then decrease.
Very good, right? It's gonna first become worse. The oscillation frequency will increase because I'm moving away from the real axis with increasing j omega d. Then it starts decreasing again here, right? So the worst oscillations happens actually at this point, right? Worst oscillations. If I keep increasing the gain, the oscillations will start decreasing this time. At minus beta, you will have no oscillations and the best settling time. Is that correct? If you keep increasing the gain, there will be no oscillations anymore, but the settling time will start becoming worse. So, in fact, minus beta is the sweet spot, right? Minus beta is where you have no oscillations, the best possible settling time. What about the steady state error? Is it 0?
No, it's not.
No, because the type of the system did not change, right? I introduced a 0. The system is still type 0. What is our type? Did we say we have a type 1 system? Oh, okay, type 0 system. Check. Okay, so we have a type 0 system. We still have a type 0 system. So still ESS is not 0 because of type 0 system. ESS will decrease with KD increasing, but a compromise between ESS and the settling time is S1 and 2 equals minus beta is the best compromise. Obviously, in order to find the corresponding gain, you need to find the break-in point. Okay, note, need to find the break-in point to find corresponding KD value, which I will not do. Okay, let's have a break. It is 10:35, 10 minutes break, and then we will be back. Okay.